Great, good morning. It's my great pleasure to introduce our next keynote speaker for the day, Carolyn Trippel from Stanford University. Carolyn is an architect, a computer architect, whose research focus is on applying formal methods and automated reasoning to improving the assurance of processor security, reliability, and correctness. And today, she is going to be telling us about hardware-software contracts for high assurance with applications to side-channel security. Carolyn.
Great. Yeah, thanks a lot for the introduction, and thanks a lot for having me. I was really honored to receive the invitation to come speak to everyone here, and I'm excited to tell you about some of the work we've been doing on designing and verifying hardware-software contracts or hardware implementations of hardware-software contracts. In other words, hardware-software interfaces that support the development of high-assurance software. And in general, by high-assurance software, what I mean is software that can support the correctness, security, and reliability guarantees, or requirements, rather, of programs. And for the most part, in this particular talk, I'm going to focus on a specific instance of this problem where high-assurance software refers to software that has been secured against hardware side-channel attacks. So to jump right into it, what is a hardware side-channel attack? So in general, these attacks involve a victim program that is running on some vulnerable hardware implementation, and it leaks its secret data to an attacker who can measure physical aspects of either its own or the victim's execution. So physical aspects can be things like program execution time, power dissipation, resource contention, and more. And so to be a little bit more precise, there's a nice telecommunications analogy that has emerged in the literature for defining hardware side-channel attacks. And it describes these attacks as featuring a so-called transmitter instruction, which is a leaky instruction in the victim program, that modulates a channel, where a channel is a hardware resource, in an operand-dependent manner, and a receiver, which is the attacker, that observes this channel modulation in order to infer the transmitter's operand value. And so in other words, transmitters are instructions that leak one or more unsafe operands by creating observable operand-dependent hardware resource usage. And so which instructions are transmitters and which of their operands are considered unsafe is very specific to a particular hardware implementation. But loads, like the one on this slide here, are very commonly assumed to be transmitters with unsafe address operands. And this is because loads often modulate data cache lines in hardware as a function of their address operands by using them as an index into these caches to decide which region of the cache to update or access. And so a receiver that's running on the same hardware as the load transmitter, say, can observe these sort of data cache line modulations as hits or misses with different access latencies for its own memory accesses that happen to map to the same cache line as the victim transmitters, and thereby, indirectly infer the load transmitter's address value. So, hardware side-channel attacks have been around for a long time, since the early 2000s at least, and the gold standard approach for protecting software from hardware side-channel attacks is something called the constant-time programming defense. And this defense relies on the availability of what I'll call a hardware-software leakage contract, or constant time leakage contract specifically. And this is a hardware-software interface that enumerates a specific hardware implementation's transmitter unsafe operand pairs. So an example is like what you see here on the slide. And these constant time leakage contracts typically include memory operations and their address operands. This is due to the presence of data cache optimizations like I just illustrated on the last slide. Conditional branches and their operands are also commonly included in these lists due to a variety of optimizations that can leak the program counter of executing instructions, including instruction caches. And then there's usually a variety of variable time arithmetic operations that you'll see on these constant time leakage contracts. Division is one common example, say to different execution paths the division might take with different execution latencies depending on its operand value, say a fast path for division by 0. All of these specific details I'm highlighting about, how a transmitter might leak its unsafe operands, those are irrelevant. And all that these constant time leakage contracts include is, this instruction you should consider as being leaky with respect to some operand value. So if you have one of these constant time leakage contracts, then what the constant time programming defense requires is that you write your programs to ensure that secret dependent data never reaches the unsafe operand of a transmitter instruction. And doing so ensures that the attacker observable executions of a program P, say that's running on some particular hardware implementation denoted by this little icon here, all attacker observable executions of that program on that hardware are indistinguishable as a function of the program's secret inputs, which is conveyed by this non-interference property on the bottom right-hand side of the slide. So as evidence of the importance of constant time programming, constant time leakage contracts have been recently adopted by industry over the last few years. And the slight difference is instead of enumerating transmitter unsafe operand pairs like I will in the slides, they enumerate non-transmitter safe operand pairs, but for all intents and purposes, we can think of it as the same thing. So to give a couple examples, ARM and Intel have these mode-enabled leakage contracts. So you put the processor into a particular mode, and then it's going to temporarily disable hardware optimizations that would leak instructions safe operands with usually some performance penalty associated with that. And then RISC-V is another example of an architecture that has dedicated instructions whose safe operands are always guaranteed to be safe and not leak via hardware side channels, so no specific mode-enabled implementation there. And so this constant time programming was long thought to be sufficient for securing constant time code against hardware side channel attacks, and as a result, it's frequently applied to cryptographic code. And one concrete example is on this slide here. There's this Salsa 20 stream cipher excerpt from the open source libsodium cryptographic library. And I've highlighted the secret dependent data in yellow in the program. And this program is constant time, so it's been written so that no secret data ever reaches the unsafe operand of a transmitter. However, this is the case in any architectural or software visible execution of the program, which traditionally are the only executions that software developers or compiler writers are expected to consider. But what happens when this program executes transiently? Like, can secrets reach the unsafe operands of transmitters in the transient executions of this program? Where a transient execution refers to the partial execution of instructions by hardware, so this is behind software's back, along wrong code paths that are eventually squashed before they've had a chance to update software visible state, aka architectural state. So to see how this, transient execution that hardware is, realizing under the covers, to see how that can cause a problem, we'll zoom into this libsodium example. And we can take a look at this call to load 32, which returns the first 32 bits of the secret key. And so this is what this load 32 function compiles down to in x86 assembly. So it's just a load of the secret and then a return. And so architecturally, this code is fine. So it doesn't, the secret doesn't leak. The caller is simply just, storing the returned value to the stack. However, what can happen at runtime of this program on hardware is hardware could mispredict the return address of this function at runtime along a wrong code path to a transient transmitter that leaks the secret. And so even though this transient transmitter, it's not going to architecturally commit and update any software visible state, it can still modulate hardware side channels in the design, which are inherently not architectural state. They're usually microarchitectural state, or state that's invisible to software. And so, for example, this load transmitter could still leak its address operand by modulating or perturbing a data cache line as a function of that secret dependent address, and this can be detected by an attacker or receiver later on. So a hardware side channel attack like this one, where the transmitter instruction, the leaky instruction, is transient due to a hardware misprediction, this is called a Spectre attack. And there are many common sources of hardware mispredictions on modern processors, with these 5 being particularly common and well studied. And the misprediction in this example is an instance of return address misprediction, or RSB for short. The acronyms are a little counterintuitive since they correspond to the hardware structures that are usually responsible for creating these sorts of predictions, but I'll usually just reference the acronyms throughout the talk. So I'm going to revisit this example a little bit later, but popping up a level. In general, any program that runs with secrets in architectural state, whether it's architectural registers or memory, is vulnerable to Spectre. And this figure decomposes all Spectre vulnerable code into a hierarchy of 4 increasingly broad classes, where the first class, I'll refer to as this architectural or arch code, which contains all code that does not hold secrets in architectural registers. So some common examples of code from this code class would be, JavaScript or WebAssembly running in a browser, or eBPF bytecode that's running in a kernel. And all of the remaining code classes besides this one can hold secrets in registers when they execute. So I'm going to skip to this constant time code class first, the CT code class. So this is code that does not architecturally leak or transmit secrets by passing them to transmitters. And many cryptographic primitives fall into this category, like the libsodium example we just saw. This static constant time code that I'll single out as a special subclass of constant time code that architecturally only places secret data in registers that can be statically typed as secret. And so examples of this code class would be explicitly typed cryptographic code, maybe written in the FACT or CT-WASM languages, or untyped cryptographic code for which a valid typing is known to exist. So this kind of code, for example, cannot feature cryptographic declassification of secrets. And then lastly, there's this unrestricted code class that, this is code that might architecturally access and leak secrets. Non-constant time cryptographic routines or much of the Linux kernel will fit into this category, but these Spectre attacks can make the secret data that's architecturally leaked by these programs much more easily accessible than if you were to rely on the program's architectural executions alone. So I'm going to talk about, some ways in which we can defend comprehensively programs from Spectre attacks. But if we want to do that, in fact, if we want to defend programs from hardware side channel attacks in general, we really do require cooperation between hardware and software. And so in this talk, I'm going to decompose this cooperation into 5 components that characterize whether or not some hardware side channel defense, or Spectre defense, can secure a particular program, where the first 2 components are implemented by hardware, and these first 2 components characterize hardware's baseline vulnerability to hardware side channel attacks. So this leakage contract component is what characterizes the transmitters on a hardware implementation, like the constant time leakage contract we saw. And this execution contract component characterizes the possibly transient control and data flow semantics of the hardware. The next 2 components, this protection set and protection mechanism, they collectively characterize a hardware side channel defense that's been layered on top of some baseline implementation, and these can be implemented in hardware or software or some combination of both. And this protection set I'm going to use to define what software visible state at each program point a defense promises to protect from leaking. And then I'm going to use this protection mechanism component to define how a defense is protecting that protection set from leaking, how it's enforcing its protection set. And then the last piece here, before I get into some more specific examples, is this secret set component, which is a property of software, and it defines what architectural state or software visible state at each program point may contain secret program data. So it's basically identifying the class of programs from the previous slide that a defense can target. And the last little piece here is, whenever a component is implemented in hardware, so I have this sort of, hardware notation here, it becomes a hardware-software contract that software relies on hardware to implement correctly. Okay, so I have 3 main technical parts to this talk. So the part 1 and part 2, I'm going to talk about some of our work on designing new hardware-software contracts that support the design of new Spectre defenses. And then in part 3, I'm going to talk about some of our work on designing what I'll call a meta leakage contract that captures all features of, I'll say, nearly all leakage contracts in use by hardware side channel defenses today, of which there are many. And in doing so, in designing this meta leakage contract, we were able to design a unified formal verification procedure for automatically confirming that hardware adheres to, any of the leakage contracts from the literature, or find bugs in cases where it does not. Okay, so I'm going to start with Cerberus, which was the first defense that is deployable on real hardware today for fully securing a slight restriction of constant time code, static constant time code in particular, against Spectre attacks involving the 5 common types of speculation from a few slides ago. And so this slight restriction of static constant time code, in addition to having this statically secrecy typable property, it also avoids passing secrets by value, so it only passes secrets by reference. And so Cerberus assumes that the hardware implements a very standard constant time leakage contract that just enumerates these transmitter unsafe operand pairs, along with a new execution contract that we proposed called ASP for Abstract Speculative Processor. And as a software defense, Cerberus implements both its protection set and its protection mechanism in software, and each of these 3 novel components is designed to address a specific challenge that is faced by all software defenses against Spectre attacks. So I'll talk about those next. So starting with this execution contract challenge, which is that compile time analysis of a program's transient control and data flow graph is intractable by default. So we solve both aspects of this challenge, but I'm going to focus mostly on the control flow aspect. And the problem is that by default, hardware can cause a program to exhibit unconstrained transient control flow. So for example, return instructions can transiently in hardware return to any instruction in the program, including ones that are hidden within compiled instructions due to variable length instruction encodings in some instruction sets like x86, for example. Further, we have function calls that can transiently jump to any instruction, including hidden ones again. And the result is this messy transient control flow graph that I don't think anyone would want to analyze at compile time. And so our solution to this problem was based on this observation that we had and others had, which is that control flow integrity extensions, or CFI extensions in modern instruction sets, an example is this Intel control flow enforcement technology. These are hardware extensions that enable software to judiciously constrain its software visible or architectural control flow at compile time. And the observation was that if software could similarly judiciously constrain its transient control flow at compile time, it could do so just enough so that the transient control flow could be reasoned about by compiler analyses. And so we had some discussions with collaborators at Intel, and we found that CET actually does have some useful transient semantics on Intel efficiency core implementation specifically. So, one line of Intel hardware does actually have nice transient semantics that we can use for this Intel control flow enforcement technology, and they've now clarified this in some new documentation in response to this work. So what are these useful transient semantics, and how do they help resolve our execution contract challenge? So to start, if we enable this Intel CET's indirect branch tracking feature, we can ensure that calls and jumps only transiently jump to end branch instructions, which are special dedicated instructions provided as part of this hardware extension. We can ensure that basically this forward edge indirect branch control flow will only ever jump to end branch instructions in the program. So it could jump to wrong end branch instructions, but it's guaranteed to only jump to an end branch instruction, and so our Cerberus defense inserts these instructions at each function entry point. Next is CET has this shadow stack feature, which combined with another non-CET feature that's called this RRSBA disable speculation control. Basically, it just prevents return address predictions from being serviced by the indirect branch predictor on return stack buffer underfills. So together, these two features can ensure that returns only return to call sites. And so Cerberus enables all three of these features. So, basically what we've done here is that we've significantly constrained the transient control flow graph of this program. The CET and, these three mechanisms here are not a Spectre defense in and of themselves, since, you can see even after we've enabled them, we still have this transient leakage of our secret that's possible in this program, but now the secret can only leak along one transient control flow path instead of a very large number of paths. So this, you don't have to look at all the details here, but this ASP execution contract we define is, just an operational model that formalizes a program's sequential and transient control and data flow semantics on hardware that implements all three of the mechanisms we just discussed for constraining a program's transient control flow, along with speculation fences and some other features that allow us to constrain a program's transient data flow. I'm going to skip a lot of details here, but at a high level, this ASP model constrains data flow speculation that arises when, so essentially it constrains data flow speculation to only permit loads to return values from wrong stores to the same address, which is something that can happen in modern hardware today. So a load might guess the address that it's supposed to access because address computation takes some time in a processor. And so we permit loads to get wrong data from stale stores to the same address, but not stores to different addresses, which is another behavior that can happen on some hardware. And then the speculation fences restrictions. So speculation fences are sort of a new term for fences that already existed in certain instruction sets, which are basically serializing instructions that require execution of all instructions before the fence to complete before the fence can execute. So they basically have the effect of terminating any ongoing transient execution before the fence can execute. So we have this model that describes all of these. We've been able to, with this model, restrict the control and data flow graph, transient control and data flow graph of a program at runtime on hardware just enough that we can defend the program from Spectre attacks. But the next thing we need to do is figure out how to do that. So, what data should we be protecting from transiently leaking at each program point to ensure that all secret data in static constant time code or a slight restriction of it is protected from transiently leaking. So prior hardware defenses in particular had prevented the outputs of these so-called access instructions from transiently leaking. So they blamed Spectre leakage of secrets in programs on access instructions, which they defined as instructions that load secrets into registers, load potential secrets into registers. But if one of these access instructions loads a secret into a secretly typed output register in a static constant time program, which is what an architectural or sequential access instruction will do, like this one that did not execute transiently, the static constant time program is already going to protect that secretly typed output register, say, from leaking. And so access instructions aren't quite precise enough. So instead, we propose to root cause Spectre leakage of secrets in programs to these instructions we call taint primitives. And they're instructions that can cause a publicly typed output register in a static constant time program to transiently hold secret data. An example, example of one of these taint primitives is a return instruction, like this one in our example, because at its transient target, a register, which you can think of as kind of an implicit output register of the return, could be publicly typed, but hold a secret value. So an example is, this in static constant time code, we have a requirement that all unsafe operands of transmitters be publicly typed. And so if this return returns to a location where there's some secret left over in this register RCX, but the location that it returned to expects public data there, we have this security type violation, we call it, introduced by a taint primitive instruction. And the interesting thing is that we can prove, and we did in the paper, that there are, first of all, taint primitives are necessary for Spectre leakage of secrets and programs, and then secondly, that there are only 4 types of instructions that can serve as taint primitives in our static constant time code when it runs on hardware that upholds this ASP execution contract. And so these are the 4 types of instructions that I can go through briefly. So first we have these non-constant address loads. So these are loads whose addresses are dynamically computed from data at runtime, and so they could transiently point out of bounds and read out of bounds secret data into their publicly typed output register. Second, we have non-constant address stores. So these are these stores can transiently, say, write secret data to an out-of-bounds memory location that's later read by a load that has a public output register. And then third, we have uninitialized stack loads. So these are loads that can actually transiently skip over initialization stores due to hardware data flow mispredictions that I briefly mentioned. And they can read stale data from a stale stack frame into stale secret data from a stale stack frame into a public output register. And then the last one is we have calls and returns, like the example we just looked at, which can be mispredicted to a wrong target that expects, a public argument in a register that holds a stale secret value from the caller or callee. So, we have this constrained set of taint primitives, and the nice thing about this is it enables us to design a novel software protection mechanism for Spectre defenses that's based on either eliminating one of these taint primitives through code transformations or preventing it from passing its outputs to transmitters' unsafe operands. And we do this latter part using speculation fences. So Cerberus implements this protection mechanism. So to block, and it does so to block Spectre attacks exploiting any combination of these 5 speculation types from the beginning of the talk. It's implemented as 3 LLVM compiler passes. So we have this function private stacks pass, which assigns distinct physical stacks to each function in order to eliminate taint primitives that arise due to stack sharing. We have this register cleaning pass that zeroes out calls and returns to eliminate interprocedural taint primitives. So this is like the return in the running example. And then we have this fence insertion pass. So this pass inserts a minimal number of speculation fences to eliminate any taint primitives that can't be eliminated by the former 2 passes. And so basically what it does is it identifies a bunch of source-sink pairs where the source is a taint primitive and the sink is some dependent transmitter along some transient control flow path in the program. And we formulate fence insertion as a minimum directed multi-cut problem, prioritizing placing fences outside of loops when we can in order to cut all paths from sources to sinks. And the effect that these speculation fences have is these taint primitives will no longer be able to transiently pass any privacy type violating output registers into the unsafe operands of transmitter instructions. So that was Cerberus. There's some pros and cons. So the pro is that it is deployable today on real hardware. It's comprehensive for hardware that upholds some constant time leakage contract, like ARM, Intel, or RISC-V hardware, and this ASP execution contract. So this is the biggest caveat. So, from talking with Intel engineers, we think there are some Intel microarchitectures that do uphold this ASP execution contract along with, featuring a constant time contract, although this is sort of yet to be formally verified on real implementations. But based on discussions, we think it's comprehensive for some hardware. And it's actually reasonably performant. So for 2 different classes of cryptographic workloads we looked at, we had 7% and 21% average overhead for these different cryptographic routines. The cons are that it's not comprehensive for most hardware. So, hardware that doesn't uphold these two restrictions, Cerberus won't be comprehensive for. It could still help you a little bit, but we're interested really in comprehensive defenses. It's also not programmer transparent, and we can debate, the degree to which we want to give up on programmer transparency, because I think it is worth doing so. But we do have this restriction that code cannot pass secret data by value. It can only pass secret data by reference, and this is really a performance decision. So we could handle code that passes secrets by value, but we'd have to insert many more of these fence instructions into the program, which are what contribute to Cerberus's overhead. So it's, as you maybe noted here already, it's not performant for general purpose code. So in cryptographic code, we generally have this nice looping structure. We're looping over some buffer and performing some computations, and we can strategically place these heavyweight fences outside of loops, but we can't do so for general purpose code. So to resolve these limitations, we very recently designed Protean, which is the first Spectre defense that is altogether comprehensive. So again, by comprehensive, just to clarify, I mean it's a defense that blocks leakage due to all transmitter and speculation types, known or unknown. It is programmer transparent, meaning no source code modifications are required, although maybe we could benefit from some. And then it is also programmable, so it's capable of tailoring its protections to the needs of any individual program. Protean assumes that hardware implements a leakage contract that's a little bit more detailed than the constant time leakage contract we've been looking at, as well as an execution contract that's able to capture all flavors of hardware mispredictions, all flavors of transient execution due to hardware predictions, whether they're known or unknown today. And I'm going to skip the details of these because we borrowed them from prior work. Unlike Cerberus, which was a software defense, Protean is a hardware software defense, where we have software define the defense's protection set and communicate it to hardware to track, and hardware implements the defense's protection mechanism. And so both of these new components are designed to address specific challenges that are faced by all prior comprehensive programmer transparent defenses from the literature, and I'll talk about those now. So this protection set challenge refers to our observation that existing comprehensive and programmer transparent Spectre defenses, which are shown in the row labels here on the left-hand side of the slide, they actually all happen to be hardware defenses as well, interestingly. So they only target one specific class of Spectre vulnerable code. And by targeting a class of code, I mean that the defense is tailored to performantly secure it. So for example, if you look in the middle here at SPT, which is one of these hardware side channel defenses that is somewhat recent, SPT is targeting, it's designed to target constant time code. And what this means is that it can secure code classes that it subsumes. Typically, it will do so with less performance overhead, but could be comparable. And then it's unable to secure any code classes that are more permissive than it, that handle secrets in a more permissive way from that hierarchy that I showed at the beginning. And so the problem with this is that if you wanted to secure a multi-class program, of which there are many important ones, like web servers and operating system kernels, you need to pick the most conservative, at least today, you need to pick the most conservative and slow defense that targets the program's most broadest code class. And so the numbers here that you see, these are the lowest runtime overheads that were achieved for a specific, for different class-specific workloads and a multi-class Nginx HTTPS web server when they're running on hardware that implements a particular defense that's capable of fully securing them, and this is all relative to an insecure baseline hardware implementation. Okay. So, why is it that these defenses can only target one code class? The reason is that they all feature these fixed hardware-defined protection sets. And these protection sets, again, a protection set is defining at each architectural step of the program's execution what data the defense is going to protect from speculatively leaking, in this case. Because they've defined these fixed protection sets in hardware, they can't be adapted to meet software's needs. And so our solution to this, protean solution to this protection set challenge is what we call the POPL'26 architectural extension. And it enables software to dynamically define and update as it executes a hardware-tracked architectural protection set. And so specifically, this POPL'26 extension, it provides a single bit instruction prefix, so 1 bit you can stick in front of instructions, that enables adding architectural registers and memory bytes to the protection set whenever they're produced or written. And then we can also, and you do this by POP prefixing an instruction. And then you can also remove architectural registers and memory bytes from the protection set when they're read or written by unprot prefixing an instruction. So currently, this POPL'26 doesn't support adding registers and memory bytes to the protection set when they're read. This is because they may have already leaked in the past, but I actually think there's some reasons to enable this feature sort of strategically in the future. One other thing too here is I drew these, explicit unprot prefixes, just to go back. So I drew these explicit unprot prefixes, but in POPL'26 binaries, the presence or absence of a prot prefix denotes, or the absence of a prot prefix denotes an implicit unprot prefix. So I'll just draw it this way. Okay, so, proteans, solution to the protection set challenge, one piece of it is this extra instruction prefix. Another piece of it is that we implemented this POPL'26 compiler, which helps us achieve this goal we had, at least initially, of programmer transparency. Hardware people in particular don't like the idea of code having to be rewritten, although I think there are, again, nice reasons to do that. And so this POPL'26 compiler, what it does is it can automatically program our POPL'26 protection set, so automatically add prot prefixes, if you will, to the different instructions in your program for any function or component given just its code class. And it just uses very simple register level data flow analyses to do this. So the pass for Arch code is the simplest. So it's just a no-op pass, so this pass does nothing. And it's nice because this code is usually untrusted. This is code that is not allowed to access secret data architecturally, so every instruction is implicitly unprot prefixed. Then we have this static constant time code pass, so it initializes all registers to secret types and applies secrecy typing rules, including that transmitters' unsafe operands must be publicly typed, and it resolves type errors by typing data as public. The constant time pass, so it can perform less unprotection than the static constant time code pass, so it can only unprotect registers that were passed to transmitters in all past control flow paths, or will be passed to transmitters' unsafe operands in all future control flow paths. So this past leaked or bound to leaked data in your program is what this pass will unprotect. And then for unrestricted code, we can do the least here from like a programmer transparent point of view. So all data is protected except for the stack pointer, constant initialized registers, and then any data that is solely computed from both, either. So, POPL'26 basically is telling hardware at each program point the architectural state that should be protected from transiently leaking, but the protection mechanism challenge involves figuring out how to protect it. And so to solve this challenge, we proved that there are two ways in which this prot-labeled data can transiently leak on arbitrary, speculative, out-of-order hardware. So one way is you could, the hardware could directly try and pass this prot-labeled data to the unsafe operand of a transient transmitter, and that's what's happening here. So we've added this register. We track protections at the granularity of full registers, so we've added this register RCX to the protection set, and here, we've jumped to this transient instruction that has directly passed this prot-labeled data to a transmitter's unsafe operand. And then there's this other type of leakage where we could have an instruction that, say, transiently unprotects some data, like this first add, and then that transiently unprotected data is passed to the unsafe operand of a transmitter. And so Protean provides two different hardware protection mechanisms with different trade-offs, different performance complexity trade-offs. They can both block these two types of leakage. They do it in slightly different ways. So one's called prot delay and the other's called prot track. And so to block this type 1 leakage, both defense alternatives are the same. So they both just stall transient transmitters whose unsafe operands are protected, like this first load, until it's guaranteed that the processor will commit them. And then to block this type 2 leakage, prot delay has a simpler hardware implementation, so it indiscriminately stalls all instructions that depend on data that was unprotected by some transient instruction until it's guaranteed that that unprotecting instruction will commit by hardware. And then prot track has more complex hardware in order to stall only transmitters whose unsafe operands depend on data that was unprotected by transient instructions. And so to block this type 2 leakage, basically in this example, prot delay will stall both of these instructions until it's sure this instruction will commit, and the prot track mechanism will only stall this latter instruction. So it gets a little bit better for performance. I'm going to skip the details of the hardware implementations. We build them by extending some prior work, essentially to be able to handle these programmable protection sets. So coming back to this slide from earlier, this has some different performance overheads for class-specific and multi-class benchmarks that are running on secure versus insecure hardware. And the takeaway is that Protean offers better performance than all state-of-the-art class-specific defenses on all workloads. Notably, this unrestricted class, which I mentioned earlier, it does perform better than the baseline. It's not exactly low overhead, but I'll talk about how we can improve this in future work. This was the code class where we could make very little assumptions based on just the code class about what data is public. Another interesting thing actually is that the performance overhead is actually not so different between the simple hardware implementation and the more complex, and I think cautiously optimistic that we could actually get the simple hardware implementation to be zero overhead with the right coordination with software. Okay, so I wanted to just touch on one last thing before I wrap up, which is, I've been talking about designing hardware-software contracts to just support Spectre defenses. We've also looked at designing hardware-software contracts to help us design verification procedures. And one verification procedure we built based on this idea was called SynthLC, and it gives us a way to verify automatically hardware adherence to virtually any of the leakage contracts in use by state-of-the-art hardware side channel defenses today. Just a quick reminder, these leakage contracts, they characterize the transmitters of the hardware implementation. So what are the leaky instructions, and potentially some more information about how they leak their operands. So we observed in this verification work that when transmitters modulate these channels or hardware resources as a function of their unsafe operands, they actually create operand-dependent execution path variability for one or more instructions. And it's this execution path variability for instructions, like that manifest, say, as a fast or slow path, that what a attacker or receiver is ultimately measuring or detecting to infer these transmitter operand values. So example is this is a very typical program pattern in a classic hardware side channel attack. We have this transmit instruction and a secret being passed to its unsafe operand. A concrete instance of this example is maybe I have a multiply instruction on hardware that implements this zero skip multiply optimization that we can describe with this little function here. And it basically just says that a multiply instruction will exhibit a fast path, like the path on the right-hand side, if at least one of its operands is 0, and it will exhibit a slow path otherwise. So multiply is kind of a hard operation to compute in hardware, so we have this fast path for easy multiplication by 0. And roughly speaking, each of these paths, I won't go into all of the details, but you can think of them as a partial, like a Lamport-style partial order on hardware events associated with an instruction's execution. So as an attacker, I can learn a function of the multiply secret operands if I know which execution path it took at runtime, and I can maybe determine this by timing the execution latencies of multiplies. So clearly, an instruction that creates and exhibits operand-dependent execution path variability is one of these transmitters that I have to worry about. This is now a slightly more subtle victim program example. So again, we do have this transmitter unsafe operand being passed to secret, and now we have another instruction executing alongside it that has a public operand. And this pattern can be exploited on this open source RISC-V processor as follows. So the victim is going to run a store to a secret address. So that's, my transmitter instruction. And followed by a load to a public address. And the load, the way it's implemented on this particular processor, it's going to exhibit one of two distinct execution paths that differ right after the load is issued to go execute. And so the load will either stall if it has an address match with a concurrently executing older store that hasn't drained to memory yet, or it will progress to access memory, wrong direction, or it will progress to access memory right away with no stall if it does not have an address match with such a store. So in this case, the attacker, right, can learn the store's secret operand if it knows which path another instruction the load exhibited. So clearly, an instruction that can create operand-dependent execution path variability for other instructions is also a transmitter. So kind of based on this observation that transmitters leak their operands by creating path variability for one or more instructions, we built this leakage contract verification procedure called synth-LC, and I'll pop that up on the slide in a second. But first of all, it takes as input a system verilog implementation of a processor, so just like a code description of a processor, instruction encodings, and some design metadata. It's mostly just we're going to use model checkers, formal model checkers, in order to do this verification process, and so the model checker needs to know how to interface with the design. And so first, this verification procedure we built, it leverages linear temporal logic property generation from a finite set of property templates that we've decided ahead of time are actually sufficient for this leakage contract verification procedure, in combination with formal model checking to uncover all hardware execution paths that each instruction could ever exhibit on the design. So for example, for the multiply, we'd uncover in this first step, this RTL to multi execution path, we'd uncover both the fast and the slow execution paths for a multiply. And we proved that by finding all instances of path variability, we've actually found a superset of all of the hardware side channels in the design that could ever leak transmitters' unsafe operands. So we've basically found a superset to all of the possible violations of this non-interference property from earlier on the hardware implementation. Next, we want to identify true positive side channels in this superset that we've gathered. And so this synth-LC component, which comes next, is conducting a symbolic information flow analysis. Again, it's using formal property generation from templates and model checking. And this time, it's trying to attribute each instance of path variability that we found earlier to one or more transmitters' unsafe operands under some hardware scheduling conditions. And so, one thing this output gives us, the one thing the output of synth-LC gives us, is we basically reverse engineered from the hardware implementation, a formally verified constant time leakage contract, all these transmitter unsafe operand pairs that are, required by many modern instruction sets today. But synth-LC is actually giving us a lot more. So its intermediate output is a complete set of what we call formally verified leakage signatures for a hardware implementation. And a leakage signature is basically just the highlighted components of what I'll call a leakage function. And this is my other hardware software contract I'm saying enables leakage contract verification. So the first part of this signature is the first part of the function name, which identifies the instruction that exhibits path variability. The second part is the step of that instruction's execution at which it subsequently exhibits a path divergence, at which the source of the variability, if you will. The return value denotes the destination execution steps of the path variability. The arguments identify the transmitter instructions that are responsible for the variability. So this N here denotes an intrinsic transmitter, meaning the transmitter and the instruction exhibiting the path variability are the same dynamic instruction instance. And then the body of the function contains the transmitter's unsafe operands that are to blame for the path divergence. So in this case, it's either operand of the multiply. And then we also get, I sort of mentioned the N superscript, but we get these superscripts for function arguments that denote different hardware runtime conditions that have to hold for some transmitter instruction to create path variability for another instruction. For example, it might be the case that the transmitter has to be older and concurrently executing at the same time as the variable path instruction in order for you to see path variability. This is the case for the store executing at the same time as the load previously. And so why am I telling you all this? So, this function is nice because all of the different components, and you don't need to understand all the details on this slide, but all the different components have these leakage signatures. They map nicely onto all of the requirements for all of the hardware features that are required to implement a variety of leakage contracts used by a bunch of different defenses. And the simple one we saw was the constant time leakage contract, but there are many more sort of nuanced variants of these, including the one that's used by Cerberus and Protean. So I'll wrap up here. I wanted to, highlight a couple opportunities that I see for continuing to improve hardware side channel defenses based on the work that we've done. So first of all, both Cerberus and Protean, they're trying to leverage information about a code class in order to determine what data should be protected from transiently leaking at runtime. But we don't leverage any explicit, say, type information present within a program, and we're generally operating with C programs where we can make very few assumptions we're just doing register level data flow analyses. We can't make any more strong assumptions like we could if we had a more strongly typed language or if we had explicitly typed variables present within our program. One thing to note actually too is with Cerberus, technically a taint primitive, it's an instruction that can introduce a secrecy type violation. And for a non-constant address load, technically a non-constant address load can only introduce a secrecy type violation if its output is public. But we actually treat all non-constant address loads as if they could have public output registers rather than filtering them, since we can't do that much filtering. We didn't find benefit from doing whatever filtering we could with just the knowledge we have within a C program. Another thing is these leakage functions or leakage signatures. They provide sort of this precise mapping from transmitter inputs to observable executions of instructions at runtime. And so we think there can be a nice way to use these leakage functions in order to, we could acquire a set of leakage functions directly from hardware and prove that they capture all of the hardware side channels and then use them to map, say, input distributions to a program to full program level observation distributions in order to do things like quantify information flow. As far as sort of hardware and software, working together, Cerberus was mostly taking advantage of our ability to judiciously constrain control flow. We took a less judicious approach to constraining speculative data flow, but there's, I think, some interesting opportunities to leverage, transient memory isolation, which may or may not be available on existing hardware. That's yet to be determined, or fine-grained mechanisms. Both of these ideas have been considered in prior work and could enable something like a Cerberus software defense to operate even more performantly than it does on more general purpose code. Also, for Protean, we right now, hardware will basically assume until it's accessed data the first time that data might be secret. It has to access some data architecturally first to know that the label it read for that data is the correct label. However, we might be able to, say, communicate labels at address translation time if we're able to encode them on pages rather than on instructions themselves, and we could avoid sort of, this declassify on access behavior that we have now and instead do declassify and address translation for lower performance overhead. And this could be paired with things like custom memory allocators in order to be assured that, say, all the data on a particular page is of a particular maybe struct type that follows a specific protect-unprotect pattern for the bytes on that page. And then lastly, this classification of transmitters that we get from the leakage functions, we can use this to, construct more fine-grained hardware protection mechanisms for side channel defenses. So right now, something like, Intel or ARM's leakage contract mode, right, will disable all these optimizations for a whole process or worse. And we could think about, say, disabling optimizations at an instruction granularity and tailoring the way we disable optimizations to be a little bit different based on transmitter types. And then one other thing here quickly on the verification opportunities. So I didn't talk about this in a ton of detail, but the interesting thing about synth-LC and some other work that we've been doing on similar topics, related topics, is we found that there's a bunch of design specifications or design requirements you might want your hardware to uphold. And one of the key bottlenecks to verifying that hardware upholds these is we rely on experts to manually write formal properties to go check against their hardware design and spend a lot of time manually decomposing those properties to get automated reasoning tools to be able to check them. And we found that for many different requirements you want your hardware to uphold, a finite set of property templates that we instantiate in a bunch of different ways is sufficient to both encode the property you want to check and decompose it to something that is scalably checkable. And synth-LC exploited this insight. We've also applied this on an industry design and saw good results as well. And I think it's applicable for the other hardware side channel attack components that we looked at today. So to kind of conclude with more of an introductory slide that I decided to stick at the end, which is, where does this work fit into the broad world? Computer systems have gotten highly complex, as we all know, and sort of in my computer architecture world, I think of this as giving rise to a couple key challenges. One is this contracts challenge, which I've mostly talked about today, which is that traditional instruction sets lack the detail needed to capture all of the ways in which hardware might undermine correctness, security, and reliability, with the focus of this talk being on security. And so, we're increasingly seeing instruction set architectures today, hardware vendors incorporating new hardware software contracts into their instruction sets in order to, try and repair or fix this problem. And then the second challenge is the verification challenge. This is sort of a staggering statistic from this. Every couple of years, Siemens EDA does this study to see how well hardware verification is going in the industry, and they found that it was actually a 20-year low of first-time silicon success, where they had over 85% of the hardware design projects they looked at had bugs that escaped into first silicon, despite them spending over half the effort on the design process. And we think this problem will continue to get worse as we solve the problem on the left, and dare I say, have the proliferation of AI tools in helping us design hardware. So yeah, this talk I focus mostly on this contract challenge. These are some key takeaways. So I think high assurance really requires us rethinking the hardware-software interface. I gave you a couple examples of this with Cerberus, Protean as hardware defenses and synth-LC as a verification framework. I do think it's worth us reconsidering what hardware and software can independently contribute to solving this problem, because I think we can kind of have our cake and eat it too, like get high performance and assurance if we have hardware software working together more meaningfully. I think in particular, finding ways to communicate rich software analyses to hardware to leverage at runtime as it executes programs gives us the opportunity to both simplify hardware and improve its assurance guarantees. And I feel these ideas are, I talked about security, but I think they're much more broadly applicable to other assurance requirements we might want our systems to uphold. All this work is open source and designed to be extensible, so definitely take a look if you're interested, and I'm happy to take any questions you have.
Hey, thanks for the talk. It was really interesting. So I've noticed that over the recent sort of decades, especially ARM have been getting really interested in providing more formal specifications for their ISAs with sort of the ASL stuff. Are you trying to integrate with that kind of ISA specification as well as sort of doing the leakage contract thing? Is there some connection there between those two things?
Yeah, good question. So the short answer is yes. So at least in our research, when we think about designing new hardware software contracts, we want them to be designed formally. So there's no ambiguity as to what the hardware software interface is that we're assuming. And so yeah, we're generally encoding everything in some sort of a formal DSL or formal language in order to make them sort of executable and unambiguous. Yeah, good question. Thanks.
Thank you for a really fascinating and an educational talk. I'm wondering about your approach to, I guess it's the SynthLC work. You're using model checking to verify the Verilog implementation. What is I guess I'm trying to understand the soundness argument. I understand that you're able to catch a lot of problems.
Yeah.
But is it comprehensive really? And have you tried to formally stitch that together to show that there's really a comprehensive?
Yeah, good question. Yeah, so the short answer, again, is yes, although right now this formal argument and proof lives in an online appendix because the architecture community doesn't care so much about that, but yes, so essentially what we did in the SynthLC work, not that they don't care, I think they like to know the formal proof exists, but they don't like to look at it. So let me go back to this really quickly here to show you. So basically what we do, here, this is what I was looking for. So basically what we do is, so this is a non-interference property encoding that, right, for basically encoding side channel safety. So your hardware is side channel safe if like the observable execution behavior is indistinguishable for any program given the same public inputs but different secret inputs. And so what we prove is if you have a receiver, an attacker, that can exactly observe the entire execution path of executing instructions, which is actually kind of a strong receiver assumption. So it's these execution paths we actually define as a partial order on the state updates, a cycle-accurate partial order on the state updates that an instruction performs during its execution. And we prove that if you have a receiver that can exactly observe for each instruction which execution path it took, that this procedure will uncover all and I'll tell you about sort of boundedness of model checking and all of that, but the procedure itself, if model checkers were perfect and didn't ever come back with bounded proofs, we would find every hardware side channel in the input design, and every hardware side channel we find would be a true positive. Now, we do get some bounded, so like one of the benefits we think of this template-based approach is we sort of ahead of time come up with a way to decompose this property into like, for the open source design we looked at, although we've reduced some of this property generation a bit to handle industry designs, but we generated about 120,000 simple linear temporal logic properties to analyze end-to-end in open source processor implementation. And each one of those properties tends to take a few seconds to minutes to check and gets unbounded proofs with the commercial tools. But there's maybe like 15% of them, this is again on the open source design, that come back with bounded proofs. And the bounded proofs will impact some of our, soundness or completeness guarantees. Like we may not find every hardware side channel in the design. I would say that's more of a completeness because the model checker couldn't search deep enough to find an execution where it was exposed. So theoretically, we have soundness and completeness, and then we have some, asterisks for modulo capabilities of the automated reasoning tool. But we're trying to do some things to resolve the incomplete results using things like integration with theorem provers and things like that. Does that answer your question? Yeah, cool. I can't see so well from the lights.
Thanks for the very nice talk. So for the second part you described, this Proteon model, if I understood correctly, this basically requires new hardware support to support these new instruction prefixes so that the hardware can do this better tracking. So I was wondering, well, A, how did you benchmark this, given that, does this hardware actually exist? And also B, is there any interest from big hardware vendors to actually add extensions of this sort to their RSA so that you can actually enjoy this on real hardware?
Yeah, good question. So first, let me start with the instruction prefixes part, actually. We chose instruction prefixes initially because, so x86 actually supports instruction prefixes. So you can add, and part of this is because they have this flexible variable length instruction encoding, you can add these prefixes to instructions, so we add this 1-bit prefix. Although I actually don't think we need prefixes per se, what we could do is say, analyze a program and store the labels for instructions in some special hardware memory that we fetch to the same time of instructions, and so we could handle instruction sets beyond those that support prefixes. So that's one thing. Two is how do we benchmark this? So we use these open source computer architecture simulators, which are these cycle accurate simulators. We use Gem 5 is one common one that has relatively detailed models that have been validated against x86 hardware. They're not perfect, but we think the relative performance benefits we get from comparing like a baseline to our defense are comparable to what we would see on real hardware. As far as industry adoption, so this paper actually will be presented in a month, so this is very new. We did try it on some industry simulators, and there does seem to be some interest, and the performance overheads we saw in the industry simulators are comparable to what we're seeing. So we're implementing actually a couple more slight extensions now, but from discussions with different industry people, there seems to be interest in this. I think particularly if we could get this, what I'm my kind of hot take or claim that we could get 0% performance overhead potentially for this, very simple hardware implementation, I think that would be a lot more buy-in. This is a fancier hardware implementation, and it costs more to implement. This one would be actually quite simple. So I think it is a cautiously optimistic, seems there's interest. Yeah.
Wonderful talk. Thank you very much. My question is if you could provide input to a new generation of systems-level languages to help in your cause, because you mentioned C had its lack of information, what would be, let's say, to keep this question short, the top 3 things you would tell a systems language designer that would help you in this cause? And if the type system is part of that, how rich or powerful of a type system would you desire, such as, say, dependent types? Thank you.
Yeah, good question. So we've been thinking about this, and so, what we've done so far, as I mentioned, is very simple. Like it's register-level data flow analyses, and we could actually get reasonable performance doing that. So the level of like sophistication we need from software is sort of unclear to me right now, but I think what is clear to me is that with more sophistication, we will get lower performance overhead, because really right now we're sort of limited by what we can communicate to hardware, how much detail, and when. So if we can also communicate detail to hardware earlier, say at allocation time rather than at access time, that would also be beneficial. As far as sort of what techniques, so I listed a couple different things here, but I think you can view them in a couple categories. So right now, we leverage information about the program's type. So like, what class does it fit in? And also just to clarify, like we're just manually going in and looking and saying, we think this code is in this type, because obviously we just have C code we're dealing with. But so we assume we have the ability to classify code. So that's like the first level, is we'd like to be able to know for sure which code class some function or component belongs to. Second is if we had, say, for example, a language that had memory safety guarantees or strong static types, we could probably do more like declassification through memory dependencies, or more on protection of data just given the code class than even what we are today. And then you could go this extra level of saying, okay, now I'm going to have explicit secrecy typing information, and that would probably do that's probably going to be the most beneficial for this unrestricted code class that I was mentioning. So I think it depends on the code class. For something like maybe a lot of functions in the Linux kernel, which are probably more in this unrestricted class, probably having explicit types and labels is going to be beneficial. For some other code classes, perhaps just the type information along with a relatively strong type system for the language could allow us to do enough type inference. That answers your question. So not 100% sure, but I think there's these different levels that might be applicable for different code classes.
We have time for just 2 quick questions.
It's really cool work. How well does the protection mechanism work when you are combining code that was compiled with and without it?
Yeah, so for code that's not, if we say don't recompile the code, the sort of formal guarantees for the code we get is something that people have called weak speculative non-interference in the literature, which means that any data that the program does not access architecturally will be prevented from leaking. But that's it. So that's, it's something. It's not, it maybe isn't perfect, but that's what you would get for, sorry, I think if I'm not close to this, you can't hear me. That's something we would get for no code recompilation, so that's kind of the minimum. And then it's kind of a pay-as-you-go model after that. So if you're, and I actually think too, kind of related to the instruction prefixes discussion, I don't think we actually need to recompile the code to get the protections we're getting here. I was thinking about this recently. We might be able to just do binary analysis and again store in like a metadata table rather than having instruction prefixes, the labels for each instruction. So we could probably even get around that a bit. But you still need to know the code class if you want to take advantage of the other sorts of. Actually, you could say, if you wanted to assume the code class was constant time, then again, sort of the, maybe it's not, but if you assumed the code class was constant time, the formal guarantee, again, that's been coined in the literature is speculative non-interference is what you would get for that program, which means that no more data than is leaked architecturally will leak speculatively. So we can kind of have those two cases.
Very nice talk, thank you.
Thanks.
I'm not sure this is going to be a quick question.
Okay.
Maybe we can just deal with the prefix of it. So for the last part, microarchitects are endlessly, annoyingly inventive, and it's.
Sorry, say that again.
Microarchitects, they're annoyingly, endlessly inventive.
Yeah.
And it was not clear to me how much of the microarchitecture you're model checking here. Is this looking just at the pipeline with some separate argument that all of the storage hierarchy is kind of irrelevant, or what's going on?
Good question. Yeah, so I'll answer. You can tell me if I'm getting the question. But we actually are model checking the full design, but there's an asterisk here. So the procedure is, let's call it semi-modular now. I think we can automate the modularity a bit now. Meaning what we can do is we can apply these approaches, say this first step of our procedure, which finds all the execution paths that each instruction can take through the design. We can apply this on like a per module level within the design. So when we applied this procedure to an industry design recently, we applied it to a module of an industry design. And we're model checking that entire module. But essentially what this first step is doing, the reason why we divide this into a find the execution paths and attribute path variability to different instructions operands, we divide into those two steps because we can use single trace properties, just looking at one copy of the design, to find all of the paths. And then we're sort of like saving this like non-interference step for once we've pruned away a lot of the details of the design. Like now we just have these abstract paths we're dealing with. These paths just contain ordering information about instructions updating individual registers within the design, like a partial order on updates to registers, but they don't contain any information about like what values they're updating the registers to. Like if you wanted, we're kind of extracting, if you will, like an ordering specification from the implementation, and then once we get that more abstract model, then we're doing the more complicated non-interference checks effectively over that abstract model. So we're model checking the full design. It's semi-modular in that right now we have to kind of manually go apply it to individual modules. In the original paper, the open source design, which is much simpler, we could look at the full core in isolation and the memory system, like the cache hierarchy in isolation. And we did those two pieces separately, and we stitched together the paths from the individual pieces, and there's some effort to stitch together the paths. And that's why I say it's kind of semi-modular. I think we can clean up with like nice interface invariants and so on, the stitching together of paths to make it less. Yeah.
I want to understand that better, but it will take longer. So
Cool. Yeah, I can talk to you more.
Why don't we take other questions offline? Just one announcement before we thank Carolyn. We're running a little bit behind, so we'll start the next session at 10:45. And with that, let's give Carolyn one.